Hello! Sometimes you want to heat just one room. However, I have a problem. We have a dog that keeps opening the door, and being far too lazy to get up and close it, I was presented with a radio-controlled car to shut the door with. But it's only tiny. See how small it is when it's placed on the palm of your hand? Now sadly, this car wasn't powerful enough to close the door, and so in this video, I'll show you how I ended up with a working solution. I started by taking the radio-controlled car apart to see what was inside. Looking at the PCB, we can see 3 chips. These two, part number TC8301, are the motor driver chips. Very simple to use, one for each of the motors. This chip, however, I can't identify as all its markings have been removed. I guess this might be some kind of dedicated microcontroller or maybe a dedicated radio chip, but it's difficult to tell. I decided to order this geared motor from Amazon. These gears reduce the speed of the motor and as a result increase its torque or strength. Now I needed to attach this to the door, but I didn't want to screw anything to it, so I designed and printed this bracket, with a special area for the motor to fit in. I used some of the leftover springs from my 3D printed joystick project to allow the motor to spring up and down a little, and at the end of the motor I fitted one of the wheels from the remote control car. Fitting this to the door to give it a quick test, I could now manually open and close the door. Nobody likes wires, right? So the next thing to do was to hook this up to the remote control car's PCB. I decided to use the motor that drove the car forward and backwards, and ignore the one turning left and right. After removing the PCB from the car, I connected it up to my motor and fitted it back to the door bracket. It all now seemed to be perfect. That was until a few hours had passed. It seemed the car had some kind of power saving that shut itself off after about 30 minutes of no use. Well, I thought, what if I use the left-right direction channel to keep the receiver alive? So I decided to use one of the spare rapid fire PCBs again from my 3D printed joystick project and adjusted its components to produce a very short pulse about once a minute. I connected this up to the remote control and managed to squeeze it inside. After resetting the system, all seemed very well. The receiver seemed to stay alive. Well, at least that's what I thought. This time, however, it looked like the transmitter would stop sending anything after a random amount of time, requiring a full power cycle before it worked again. It was almost like the transmitter chip was locking up or something. So, it looked like the entire remote control circuit was going to be of no use whatsoever. I couldn't work out what the main chip was doing as all the numbers had been removed. I guess I'll just have to build something myself, and I wondered, is it possible to do this without using an Arduino or a microcontroller? And the answer is yes. I started looking at these 433 MHz transmitter and receiver modules. You put data in and you receive data out. On their own, however, this isn't good because there's so many other devices constantly transmitting on that frequency, we need a way to work out which data is ours. Now you could use an Arduino to receive and transmit something to check the data is okay, and in fact there's a specific library available for that. But again, I wanted to see if I could do this without an Arduino. But then I discovered the HT12D and HT12E encoder decoder chips. These chips can be programmed with an 8-bit address to help isolate them from anything else, and then will transmit 4 bits of data. Now supposing I use one of the inputs to mean go forward and another one to mean go back. Well, that should work. I need the motor to be in 3 states: off, backwards, or forwards. Now I can't just connect the motor up to the chip. It's not designed to drive this amount of power, so I started looking for some kind of motor driving chip, remembering what I'd found on the original PCB, and I found the L9110H motor driver chip. This can be used a bit like the H-bridge circuit, meaning it will source and sync current at 0 or 5 volts. It's not a simple switch. So if I connect this to the 2 outputs of the transmitter, then if they're both the same, the motor will be off, and if one of the pins changes state, the motor will move. Perfect. Lastly, I want the receiver to run from an 18650 battery, so I connected it up to a simple charge controller and a battery protector PCB, but the receiver board needs 5 volts. So the simplest thing to do was to get a DC to DC buck boost converter board. This tiny board produces 5 volts output as long as the input is between 3 and 12 volts. Perfect for the range on these lithium batteries. The final circuit for the receiver looks like this. It looks a little complex, but most of it is pre-built PCBs, so it should be simple to assemble. Pay specific note to the 68K resistor. It won't work if you change this value. You can also use these pins high or low to create a unique address for this decoder, but you must make sure you match the same pattern on the transmitter. Now onto the transmitter. This is fairly simple, and what's more, it doesn't need to be ran at 5 volts. I want 2 buttons. One for open and one for close, but I don't want the transmitter running unless I press one of the buttons. Now I could use buttons with multiple contacts so they turn the power on when pressed, but I didn't want to do this. Instead, I decided to use multiple diodes arranged such that each will connect the data pin to ground as well as the chip and the transmitter PCB. And combining this all up, we end up with this circuit. The only issue is when you release the buttons, the motor will carry on moving as the receiver will keep outputting the last state. Easy fix, I added a capacitor to keep the transmitter powered up for a short amount of time after the release of a button. Again, pay attention to the 1 megaohm resistor. If you change this value it will not work, but more about this later. And once again, remember to set these pins to the exact same configuration as the receiver. After connecting it all up, it worked, but it had a range of about 5 centimeters, and that's not particularly useful. So the first thing to do is add an antenna to the transmitter and receiver, and there's a bit of science to this. I'll be using a piece of wire as an antenna, and this is known as a whip antenna. But to make it the most sensitive, the length becomes very important, as it should be some multiple of the wavelength of the frequency. I'll choose an antenna length of about 164mm, not being too concerned about the accuracy, but the closer the better. After connecting them, the range was better. I got about half a metre, but that's still not great. So the only alternative is to boost the power in the transmitter, and here's where things become a little bit more tricky. Because these encoder-decoder chips need to be running at the same oscillator frequency, and that frequency is determined by a resistor and also the voltage. So I switched out the rechargeable 18650 to a standard 9V battery, but now we have to change the resistor in the transmitter too. If we take a look at the datasheets for the HT12D and the HT12E, we can see these graphs at the bottom. These tell you the oscillator frequencies for a given resistor and voltage. It doesn't need to be perfect, just roughly. And these diagrams can be a little bit confusing at first until you understand how to use them. Now I could change the resistor in either the transmitter or the receiver, but I've decided to only change it in the transmitter. So the receiver is going to be running at 5V, and we're using a 68K resistor. If we plot this on the graph, you can see where they cross we get an oscillator frequency of 125 kHz. According to the datasheet, the decoder chip needs to run 50 times faster than the encoder. So 125 divided by 50 gives us 2.5 kHz. And we're going to run this from a 9V battery. We'll ignore the diode voltage drop as it won't make that much of a difference. We then need to choose a suitable resistor value for where these two cross over, and I know there isn't a line there, but I guess we could work out where it should be, and that appears to be approximately 1.3 megaohms. So if I add another resistor, say 330 kiloohms in series with the 1 megaohm resistor, this should be about right. This makes the final transmitter schematic now look like this. And once soldered in, we now had a range of about a metre. But there's a flaw in my design. The motor stops properly if you release the button, but if you go out of range whilst pressing the button, the motor will keep on spinning. Fortunately for us, the decoder chip has a pin labelled valid transmission, which we can use to only operate the motor when a valid signal is being received. This pin cannot provide enough current to drive the motor, but we can use it to control a MOSFET that provides power to the motor driver chip. Making this modification now gives us the following circuit. I've also added an activity LED so you can see when it's getting a valid signal too. And the MOSFET I'm using is probably way overkill, but it's what I had lying around. Now a big pile of wires isn't very nice, so what I needed to do was to make it look more presentable. And I did this by printing a simple box for the controller. And here they are assembled, and here's the transmitter assembled and screwed together. Looks quite good. Now for some testing. First, I'm just going to test it on the desk. You can see the buttons control the motor direction perfectly fine. And for the fun part? Well, on the actual door. Well, it works mostly, but the range is still quite poor. Yeah, okay, so a little bit different from my usual videos, but sometimes it's nice to try and build something with just electronics and no microcontrollers. I've often seen Arduinos used for things that clearly basic electronics would do instead. Now I'm not overly impressed with the performance of these transmitters and receivers, so in future I may look at a better and simpler alternative. I hope you've enjoyed exploring this with me. Thank you for watching, and I'll see you in the next one.